Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to look at the shooting method. So in this topic, we will describe the shooting method. Specifically, we will explain how to convert a boundary value problem into an initial value problem. We'll discuss what appropriate slopes we should start with for these initial value problems, and then we will see how we can find such solutions with our initial problem solver DP45. We will then explain how we can use these results together with the secant method to get an even better approximation of the initial slope that will give us hopefully a better solution to the boundary value problem. Finally, we will look at the special case where the ODE is a linear ODE. Now, the technique we're going to look at first is commonly referred to as the shooting method, specifically because it refers to how one would try to hit a bullseye at a significant distance without adjusting sights. So suppose you're aiming at a target and you're trying to hit that target at, say, 1 kilometer. Now, once you're firing over 300 meters, unless you're firing a laser, the projectile is going to follow a path as affected by gravity, wind, air resistance, tumbling, imperfections, temperature, and, interestingly enough, yes, the Coriolis effect, the fact that the Earth is spinning, which in the northern hemisphere will have the nasty habit of moving the target to either the left or the right of your point of aim. So how would you try to hit such a target? Well, let's say you aim for the bullseye, and assuming that your breathing is correct and you let the round go, it strikes to the right and low. So what do you do next? You correct. You correct by aiming to the left and up. So you fire again. Now you're closer to the bullseye, but now you're a slight bit to the left and up. So once again, you correct, and hopefully now your third shot will hit the bullseye. Now suppose that we have a boundary value problem in this form. Well, if there is a solution, that solution must have a slope at the left-hand endpoint, that is at x equals a. Now, we don't know what that slope is. However, suppose we convert this above boundary value problem into an initial value problem, where we now specify the value of the function at a and the initial slope. Now, this now becomes an initial value problem. The problem is, if I just pick an arbitrary s for an initial slope, there's no guarantee that the solution to this initial value problem has a value at the value x equals b equal to our right-hand boundary condition u sub b. Thus, we have a goal. Our goal is to find that initial slope, let's call it s sub b, such that the solution to this particular initial value problem also satisfies the boundary value problem we were trying to solve initially. Now, up until this point in this course, we've always formulated our questions in terms of some sort of mathematical expression. For example, for what values of x does this left-hand expression equal, for example, the value 0.3? The question above is also a numeric question, but it's much more complex. We can't just evaluate an expression. Basically, we are saying find that slope s such that if you find the solution to this initial value problem, it also has the condition that when you evaluate this solution at b, it equals u sub b. That is, given an initial slope s, we must approximate the solution to this initial value problem. Sounds like Dorman Prince might be a good idea here. So this is just an equation in one variable s to which we don't know the solution, but we'd like to find that value s, or at least approximate it. All right, what did we say before if we had an equation? If we had a nonlinear equation, and this is definitely nonlinear, then what we want to do is convert this into a root finding problem. Find that value of s such that this expression is equal to 0. Thus, given an initial slope s, we're going to calculate the solution, evaluate at b, and subtract off the value u sub b. If this is indeed 0, then we have found the appropriate initial slope, which gives us a solution to the boundary value problem. Now, if this expression is less than 0, then that means the value of the solution evaluated at b is less than the desired value we're targeting for. Consequently, we should choose a larger initial slope for the next try. On the other hand, if this expression is greater than 0, that implies that the solution at b is greater than the desired solution, so we should choose a smaller slope. Sounds like a root finding problem, doesn't it? Question is, how much larger or smaller? Well, we're not going to be able to use Newton's method in this case because we have no clue what the derivative is. How much does the value of the solution at b change if we change the slope? Again, this isn't something we can calculate. However, we do have another method. We have the secant method, and that doesn't require us to calculate the derivative. Now, the secant method requires two initial slopes, or two initial values to start working with. So we don't know what the solution is, but say we have these two endpoints as being the boundary values that we are seeking. So what should we choose as an initial slope? Well, looking at this, doesn't it make sense that we should choose as the initial slope just the slope between these 2 points? So our initial slope is going to be exactly this, the difference in the target values over the width of the interval. That gives us the slope of this connecting line. Now the secant method, however, requires two initial values. So the first initial value should be the slope between those 2 points. What do we choose for the second initial value? Well, let's approximate the solution for the initial value problem with the initial slope we see here. Now, that's probably not going to end up equaling u sub b when x equals b. It will be some other value. However, we're either going to overshoot or undershoot u sub b. Well, in this case, I'm giving an example where we have overshot. Well, in that case, why don't we aim for a point that far below the initial value? Okay, so let's take that slope. So consequently, our second slope is going to be this expression here. So that is the slope between that second point there and the original point a with the value u sub a. All right, now we can iterate. So given s sub k as an initial slope, we simply approximate the value of the solution with this initial slope at x equals b. So the value we see here. Now, recall that if we were trying to find the root of g of x, and we had two approximations, x sub k minus 1 and x sub k, the next approximation would be the value you see here. Well, in this case, we're just finding the root of this more complex expression. So, substituting in this expression, we have that the next slope we will use is the previous slope minus this expression. Simplified, this works out to the expression we see here. Now notice, all we're going to do is calculate two solutions to the initial value problem and evaluate those at b. We'll substitute those into this expression, and that will give us the next slope we should be using. So it looks ugly, and it takes a lot of work to find each of these values, but once we have them, we just substitute in and calculate. Now let's look at this visually. We calculated some initial slope. All right, so then we find the solution to the initial value problem with that initial slope, and we evaluate that solution at b, and we compare it with the target u sub b, or the right-hand condition of the boundary value problem. In this case, that is positive, and therefore we really want to try a smaller slope. So we described an equation for calculating this next slope, which in this case is going to be a smaller value. Now we can find an approximation to this initial value problem with that initial slope, and we can evaluate that at b and compare it with the right-hand value of the boundary value problem. All right, it's a little bit closer, and so now we can apply the secant method, and the solution to the secant method will be our next slope. We'll repeat this process at S2, and then we will use the errors at S1 and S2 to find the next slope we should use, and so on and so forth. All right, let's look at this from another point of view. Here are the boundary conditions. Now, we first start by determining the appropriate slope, and we said that that would be the slope between the 2 points. All right, that's our initial slope. We find the approximation to the solution to the initial value problem that has that initial value and initial slope, and we evaluate that at b. And it's almost certainly not going to be the right-hand value of the boundary value problem. However, we saw how to take that and to use that to calculate a new slope S1. So basically we undershoot by approximately just as much as we overshot. So there's S1. Okay, well now we calculate the solution that has those two initial conditions, and hopefully we are closer to u sub b. All right, so now we have those two approximations, and now using the secant method, we can determine S2, which will hopefully give us an even better initial slope and a better result. So when we approximate it with that new initial slope, hopefully we are now even closer to the point u sub b when x equals b. And then we just continue to repeat. All right, so how are we going to do this? Here we have our boundary value problem. We're going to convert this into an initial value problem. Let us define two unknown functions, w0 and w1. w0 is the unknown solution u of x, W1 is its derivative. We can now define a vector-valued function of the variable x, and we can differentiate it. And differentiating it, we get that the derivative of W0 is W1, and the derivative of W1 is the right-hand side of the ordinary differential equation evaluated at x and the vector-valued function w of x. Our initial condition is the vector u sub a and s, where again we will be choosing different values of s as the initial slope. You will see that this is now a transformation from a boundary value problem into a system of two first-order initial value problems. Now all we have to do is find the value s, using the technique we described before. All right, for our implementation, suppose we have the following boundary value problem. We can define the following values. We can also define the following function that describes the right-hand side of the ordinary differential equation. So du times u plus x plus 1. All right, now that defines the right-hand side of the ODE. However, we need the right-hand side of a system of two first-order initial value problems. So we have a vector-valued function of both the space variable x and the vector function w. And of course, the derivative of w0 is w1, so that's the first entry returned. The derivative of w1 is the function f evaluated at x, the value of the function w0, and its derivative w1. We can also indicate our initial guess for the slope, and that's just going to be the slope between the two endpoints of the boundary value problem, whatever that works out to be. Now we can call dp45. Again, the system of first-order initial value problems is defined by the function capital F, which we just described previously. The interval over which we are approximating is from A to B, and the initial conditions are the vector with the value u sub a and our initially calculated slope. The next argument is, of course, the range over which we will allow h to vary over, and then the absolute epsilon value. The last argument, true, indicates that we want dp45 to explicitly end right at B and don't go any further. All right, so now let's get the first argument returned. Recall that dp45 returns a tuple of 4 values. The first value is the number of intervals into which the interval AB was broken up into. What this means, of course, is that each of the arrays of data will have n plus 1 entries. All right, so we now have that value n. Now let's make sure that the x values go from A to B. So the last x value, and remember that the x values are returned as the second entry of the tuple. That's going to be an array of n plus 1 doubles, which are the times at which we are approximating, or in this case, the x values at which we are approximating the solution at, and the last of these x values should be equal to b. Finally, the third entry of the tuple that is returned is an array of n plus 1 vectors. So we want the last vector in this array, and the two entries of that array are the value of the function and the value of the derivative. Well, we only care about the value of the function, so we only want the 0th entry of that vector. All right, so this now gives us the value of the function at b when the initial slope is s0. Well, now we can calculate the value of s1. So we either overshot or undershot. It's almost certain that we did not hit u sub b exactly. So once again, we will calculate the next slope using the previous formula. So if we overshot by a certain amount, then we will try aiming a little bit lower. If we undershot, we will aim higher. We can now call dp45 again and just assign the result to the local variable result. After all, it's already been declared to be of the appropriate type. The only difference now is that the initial condition for the vector is u sub a and the now calculated slope s1. Everything else is more or less the same. Once again, let's get the number of subintervals in this solution. After all, the number of subintervals may change. We will assert that the x value at the end is indeed b, just to make sure. And then we will extract the value of the solution at x equals b when the initial slope is s1. We'll assign that to u1b. All right, so now we have two initial slopes, s0 and s1, and we have the value of the functions u0b and u1b. You'll recall that we determined the appropriate expression for the secant method to determine the next slope, and that is shown here. And now we would simply repeat this whole process over and over again until successive approximations, or the value of the function evaluated at b, is close enough to u sub b. What does this look like as an iteration? Well, let's just look at this. We determine and assign the two initial slopes s0 and s1. We're then going to have a loop that iterates at most max iteration times. We get the result with the current value of s1, and we get the value of this solution at b. Now, if the value is sufficiently close to u sub b, and I'm assuming we're using the same absolute epsilon, then we are done. We can either return or continue to use the current solution we just calculated. If, however, we are not done, we just calculate a new slope, and then we discard s0. S0 becomes s1, and s1 becomes s2, the newly calculated slope, and we repeat again. This is essentially the secant method. Alternatively, of course, if you've already implemented the secant method, you could instead rework the previous functions to simply appropriately call the secant method. Now, as for some humor, the Wikipedia page for the shooting method actually only suggests using either the bisection method or Newton's method explicitly. There's only a problem with this, because the bisection method requires that we've already bounded the solution. So we have to have two initial slopes, one that overshoots and the other which undershoots. We're not guaranteed we have that, and it may actually take a little bit more work to find two such slopes. Also, Newton's method only works if we can calculate the derivative. I personally don't know how much the evaluation of the right-hand endpoint of the solution to the ordinary differential equation changes as the initial slope changes. That, I think, would be rather difficult to calculate. I'd be fascinated to know if such a method does actually exist. Now, here's one nice result. If the ODE is linear, we are guaranteed that we only have to perform one iteration of the secant method, and it immediately converges. Not only that, there is a unique solution. One more awkward result, however, is that if the ODE is not linear, then the solution may also not be unique. So we may actually find two or more solutions to the same boundary value problem. So following this topic, you now understand the idea behind the shooting method. You know how to convert a boundary value problem into an initial value problem for which we have to determine the appropriate initial slope. You know how to determine two initial slopes based on the boundary value problem. And you understand how to apply the secant method to get subsequent better approximations. You're also aware that the secant method needs only one iteration if the ordinary differential equation is linear. Acknowledgements, the colophon, and a disclaimer. Cheers!